The James Webb Telescope has made groundbreaking discoveries in astronomy in recent years, giving us a fresh viewpoint on space. The JWST also investigates the atmosphere of the planets outside our solar system and searches for signs of extraterrestrial life. The publication of the clearest photograph of Proxima b, a potentially habitable exoplanet located just 4.2 light-years away from Earth, is one of the most recent thrilling discoveries. What secrets does this distant world hold? Can it hold life? Join us as we look into the clearest image of Proxima b released by the James Webb Space Telescope. The clearest image of Proxima b revealed. Proxima b, commonly known as Proxima Centauri b, is a planet in the habitable zone of its parent star, Proxima Centauri. It is located in the Alpha Centauri triple star system, which is the closest star system to our own. It was discovered in 2016, and since then it has piqued the interest of astronomers due to its proximity and possibility for livelihood. Proxima Centauri is classed as an M-type red dwarf star. Despite being our nearest star neighbor, due to its low apparent magnitude, it is not visible to the human eye. It is, nonetheless, a star worth admiring because it is one of the most efficient in terms of energy generation and will continue to be a main sequence star for another 4 trillion years. It receives roughly the same amount of radiation from its star as Earth does from the Sun, raising questions about the presence of water and the possibility of life on its surface. The habitability of Proxima b, on the other hand, is still being contested, as it receives severe ultraviolet radiation from its star, rendering it hostile to life as we know it. Thanks to a recent study using high-resolution magnetic field maps, we have better understood the solar wind and the dire situation of Proxima b. The study reveals that this planet receives roughly 1,000 times more solar radiation than the Earth, which will put any potential habitat in danger of powerful flares. A Proxima Centauri flare in April 2021 was 100 times more potent than any flare ever observed from the Sun, which makes it hard to believe that life exists there due to intense radiation without a specialized shelter. The idea of residing on a planet orbiting Proxima Centauri is inviting, but the reality is far from hospitable. Furthermore, the discovery of Proxima Centauri b, a planet at habitable distances from the nearest star to the solar system, was a breakthrough in planetology and has heightened interest in the Alpha Centauri star system, of which Proxima Centauri is a member. Proxima Centauri b is thought to be the best-known exoplanet as of 2023. Proxima Centauri b orbits its parent star at about 0.05 astronomical units, which is around 7.5 million kilometers, and has an orbital period of about 11.2 Earth days. Its additional attributes are unknown, although it is thought to be a potentially Earth-like planet with a minimum mass of at least 1.07 and a somewhat greater radius than Earth. The planet orbits within the habitable zone of its parent star, but its atmosphere is unknown. Proxima Centauri is a flare star with powerful electromagnetic radiation emissions that could deplete the planet's atmosphere. The planet's close vicinity to Earth provides a potential for robotic space exploration, such as the Breakthrough Starshot project. As humans, we've always been fascinated with the idea of encountering extraterrestrial life, and in late 2020 the desire heightened when a peculiar signal from the Alpha Centauri system was found. Interestingly, the signal reads that at an unusual frequency of 982 MHz, which is not typically associated with waves from Earth-based satellites and spaceships. There was a divided opinion on this unfamiliar prompt among the experts. Some speculated that a piece of manufactured equipment might have caused the prompt, while some believed it might be proof of supernatural life. So traveling to Proxima Centauri, the closest planet to Earth, to find aliens may not be as far-fetched as one thought. The breakthrough initiatives have been researching the likelihood of cutting down travel time from hundreds of years to just decades. New research points out how current technology could potentially overcome the challenge of accelerating an object as its mass increases, particularly as it approaches the speed of light. Despite this, Alpha Centauri being the closest star to the Earth would still require 6,000 years of year with available technology, making it a formidable journey. Starshots, a project aimed at reaching the Alpha Centauri system, is contemplating using lasers to propel a spacecraft towards its destination. However, the main challenge is in the Earth's atmosphere, which affects incoming lights and laser lights, making it difficult to exert the necessary force to move a spacecraft forward. Babatunde, the paper's first author, suggested that adaptive optics could be used in reverse to overcome the challenge. Small lasers on satellites would assess atmospheric effects in real time, which will allow much more powerful lasers on the ground to maintain a tight focus on the space probe. The required lasers need a large amount of 100 gigawatts of power to send the vessel at any given time, which is equivalent to the entire electricity consumption of the United States. However, the lasers only need to run at a maximum capacity of 10 minutes, and to spread the electricity across a kilometer region, they plan to use 100 million lasers. The Starshots team is determined to push the boundaries of space exploration. The object hurtling through space will be moving at the astonishing 20% of the speed of light when the lasers are turned off. The spacecraft would be a little over 10 meters in diameter and could reach the Alpha Centauri system in just 22 years. However, the gravitational pull of the Sun and interstellar debris may considerably slow it down. Even if the spaceship reaches Alpha Centauri, its feedback will take another 4 years to reach the Earth. Babatunde and Sibley, who are part of the Starshots, know that keeping the probe from melting is one of the challenges of this discovery. To prevent this, the mirror on the spaceship must be practically perfect, reflecting 99.99% of the light that strikes it. Additionally, it needs to double the momentum transfer while decreasing heat in a matter of days. Once launched, the probe would traverse the Alpha Centauri system, likely never getting close to the planet. What's fascinating about this concept is that once the launch system is in place, more inquiries may be sent for a reasonable price. The chances of catching a fleeting glimpse of any Earth-like planets are significantly increased if a fleet of discoveries floods opposite the planet system. So, if mankind can arrive safely on Proxima Centauri, we will be able to explore more about the planet and the availability of exoplanets. In 1992, scientists made the first official findings of planets circling a particular class of neutron star called a pulsar. 3 years later, the first planet revolving around a star similar to the Sun was found. Since then, numerous additional planets have been discovered, including several Earth-sized worlds within the habitable zone of their stars. Intervention of James Webb Space Telescope. The James Webb Space Telescope, fondly referred to as the JWST, enables astronomers to study the early universe and better understand the origin of galaxies, stars, and planets. Researchers can analyze the hues in those images by using the telescope's camera and filters to gather a specific range of light colors. The JWST's ability to look further back in time and space than ever before has led to significant findings on the evolution of erosion. Astronomers face considerable obstacles when observing exoplanets like Proxima b. The James Webb Telescope, which debuted in 2018, shows great promise for investigating Proxima b. The presence of an atmosphere on an exoplanet, however, does not ensure the possibility of life, as it might be comparable to Venus, with a thick and unsuitable atmosphere. Webb will employ the transit method to research exoplanets, which means it will look for dimming of a star's light as its planet passes between us and the star. This is referred to as a transit by astronomers. Collaboration with ground-based telescopes can assist in calculating the mass of the planets using the radial velocity technique, that is, detecting the star wobble generated by a planet's gravitational attraction, and then Webb will perform spectroscopy of the planet's atmosphere. The telescope will also be equipped with coronagraphs, which will allow direct imaging of exoplanets near bright stars. An exoplanet image would be only a place, not a big landscape, but by examining that spot, we can learn a lot about it. This includes its hue, seasonal changes, vegetation, rotation, weather, and so on. The science of measuring the intensity of light at different wavelengths is known as spectroscopy. Spectra are graphical representations of these observations that hold the key to understanding the composition of extraterrestrial atmospheres. The starlight travels through the atmosphere of a planet when it passes in front of it. If the planet, for example, has sodium in its atmosphere, the star's spectrum, when combined with the planet's, will result in an absorption line in the spot in the spectra where we would expect to see sodium. This is because different elements and molecules absorb light at different energies, and we can predict where in a spectrum we could expect to find the signature of sodium, either methane or water, if it is there. Why is an infrared telescope essential for characterizing these exoplanets' atmospheres? The advantage of making infrared studies is that molecules in the atmospheres of exoplanets have the most spectral characteristics at infrared wavelengths. Infrared image analysis is the major method used by scientists to examine Proxima b. This is done by catching reflected infrared light. The JWST's strong infrared vision detects worlds beyond our solar system. Scientists can determine whether Proxima b contains water or is enveloped by an atmosphere by looking for patterns in these photos. This groundbreaking approach opens up a new world of possibilities and paves the way for future superterrestrial research. The inquiry into Proxima b is centered on the discovery of its water content and the presence of an atmosphere. The presence of water on Proxima b improves the prospect of habitability. Furthermore, the presence of an atmosphere may protect the planet from high surface heat while transferring heat to the planet's dark side. The ability of the JWST to examine infrared images becomes critical in determining these parameters. However, given the complexity of planetary atmospheres and the limitations of present technology, obtaining definitive answers remains difficult. While the presence of an atmosphere is important in determining the habitability of a planet, it does not ensure the presence of life. A dense atmosphere like Venus, as scientist Ed Turner points out, does not support life as we know it. As a result, the mere presence of an atmosphere on Proxima b does not guarantee its habitability. To get a thorough grasp of this strange world, scientists must apply a variety of methods and observations. The comparison of Proxima b and Venus is critical in comprehending the difficulties in studying potentially habitable exoplanets. Venus has severe temperatures despite having an atmosphere nearly 90 times denser than Earth's. This example serves as a reminder that habitability is the result of a complex interaction of several elements. Studying Proxima b provides a once-in-a-lifetime opportunity to learn about the complexities of planetary atmospheres and the circumstances required for life to thrive. The finding of Proxima b is a huge step forward in our quest to find planets outside our solar system that may host life. The potential of the JWST to collect photos of worlds other than our own opens up endless possibilities for future exploration. Despite its young age in comparison to Earth, Proxima b stands as a testament to the vastness of our universe and the possibility of life in far corners of space. Proxima b, in comparison to our 4.5 billion-year-old Earth, is still in its infancy, estimated to be between 15 and 20 million years old. This young age poses intriguing issues concerning the genesis and evolution of the planet. Sasha Hinley, an associate professor of physics and astronomy at the University of Exeter, conducted observations that shed light on Proxima b's categorization as a gas giant. The planet's absence of a rocky surface makes it improbable to support life as we know it. However, more investigation and research can provide a better knowledge of its distinctive qualities and shed light on its habitability potential. Physical properties of Proxima b at 4.2 light-years. Proxima Centauri b is the nearest exoplanet to Earth. It orbits Proxima Centauri every 11.186 Earth days at a distance of around 0.049 astronomical units, which is more than 20 times closer to the Sun than Earth is to the Sun. It is unknown whether it has an eccentricity as of 2021. However, Proxima Centauri b is unlikely to be ubiquitous. The planet's age is unknown. Proxima Centauri may have been grabbed by Alpha Centauri and hence may not be the same age as the latter pair of stars, which are approximately 5 billion years old. Moons on Proxima Centauri b are unlikely to have stable orbits. As of 2020, the estimated minimum mass of Proxima Centauri b is 1.1730.086 Earth masses. Other estimates are similar, with the most current estimate being at least 1.070.06 Earth masses, although all values are minimal because the planet's orbital inclination is unknown. This makes it similar to Earth, but the planet's radius is unknown and difficult to calculate. Estimates based on possible composition give a range of 0.94 to 1.4 radius, and its mass may border on the cutoff between Earth-type and Neptune-type planets if it is lower than previously estimated. Depending on its composition, Proxima Centauri b might be anything from a Mercury-like planet with a big core which would necessitate specific conditions early in the planet's lifetime to a Jupiter-like planet. The phase-EMG ratios of Proxima Centauri are expected to roughly match the ratios of any planetary bodies in the Proxima Centauri system, and various observations have found solar system-like ratios of these elements. As of 2021, nothing is known about Proxima Centauri b, except for its distance from the star and orbital period. However, several simulations of its parameters have been performed. Several simulations and models based on Earth-like compositions have been developed, including predictions of the galactic environment, internal heat generation from radioactive decay and magnetic induction heating, planetary rotation, the effects of stellar radiation, the number of volatile species the planet contains, and the changes of these measures over time. If it formed at its current distance from the star, Proxima Centauri b most likely formed under different conditions than Earth, with less water, harder impacts, and a faster overall development. The amount of material in the protoplanetary disk would be inadequate to construct Proxima Centauri b at its current distance from Proxima Centauri. Instead, the planet, or protoplanetary fragments, most likely formed at a greater distance and subsequently traveled to Proxima Centauri b's current orbit. It may be high in volatiles, depending on the nature of the precursor material. A variety of creation scenarios are feasible, many of which are dependent on the presence of other planets in the vicinity of Proxima Centauri and would result in diverse compositions. Proxima Centauri b is most likely tidally locked to the host star, which means that for a 1:1 orbit, the same side of the planet would always face Proxima Centauri. It is questionable whether such conditions can exist, as a 1:1 tidal lock would result in a severe climate with just a portion of the planet habitable. The planet, however, may not be tidally locked. If Proxima Centauri b's eccentricity was more than 0.1 to 0.06, it would tend to enter a Mercury-like 3:2 resonance or higher-order resonances such as 2:1. Additional planets in the Proxima Centauri system, as well as interactions with Alpha Centauri, could excite higher. Even with low eccentricity, a capture into a non-tidally locked orbit is feasible if the planet is not symmetrical. A non-locked orbit, on the other hand, would cause tidal heating of the planet's mantle, increasing volcanic activity and possibly shutting down a magnetic field-generating dynamo. The precise dynamics are heavily influenced by the planet's interior structure and its evolution in reaction to tidal heating. Exoplanets can range from gas giants to terrestrial planets similar to Earth. There are numerous exoplanets waiting to be discovered in the universe. Hot Jupiters and Neptunian exoplanets are among the gas giants that have piqued the interest of astronomers. The discovery of exoplanets rekindled humanity's interest in space exploration and the prospect of life beyond Earth. While many variables make Proxima b inhospitable, the search for life on other planets continues. The James Webb Space Telescope is critical in this search, giving information on the composition and possible habitability of these distant worlds. The first exoplanets were identified in the early 1990s, but 51 Pegasi b, a hot Jupiter circling a Sun-like star 50 light-years away, was the first to make headlines. 1995 was the watershed year. Dozens more have been uncovered since then. Size and mass are important factors in defining planet type. There are also variations within the size/mass categories. Scientists have also discovered an unusual gap in planet sizes. The Radius Valley, also known as the Fulton Gap, was named after Benjamin Fulton, the principal author of a paper that described it. Data from NASA's Kepler mission revealed that planets between 1.5 and 2 times the diameter size of Earth are uncommon, placing them among the super-Earths. Worlds that reach this size quickly attract thick atmospheres of hydrogen and helium gas and balloon up into gaseous worlds, whereas planets smaller than this limit are not large enough to hold such an atmosphere and remain primarily rocky, terrestrial bodies. Smaller planets that orbit close to their stars, on the other hand, could be the cores of Neptune-like worlds that have had their atmospheres stripped away. The inner and outer look of each asteroid type changes based on its composition. Gas giants are planets the size of Saturn or Jupiter, our solar system's largest worlds, or much, much larger. Within these broad groups, there is more variability. Hot Jupiters, for example, were among the earliest discovered planet types, gas giants orbiting their stars so close that their temperatures jump into the thousands of degrees, either of Fahrenheit or Celsius. These massive planets have such close orbits that they generate a noticeable wobble in their stars, pulling them about and generating a quantifiable shift in the spectrum of light from the stars. In the early days of planet hunting using the radial velocity method, this made hot Jupiters simpler to find. These gas-dominated planets, similar in size to Jupiter, rotate incredibly near their parent stars, circling them in as little as 18 hours. Nothing like them can be found in our solar system, where the nearest planets to the Sun are rocky and orbit far farther away. Neptune planets are similar in size to our solar system's Neptune and Uranus. They will most likely have a diversity of interior components, but all will have outer atmospheres dominated by hydrogen and helium and rocky cores. They also discover mini-Neptunes, planets that are smaller than Neptune but larger than Earth. There are no planets of this size or type in our solar system. So scientists are still learning about them. The James Webb Space Telescope's launch in December 2021 has given astronomers a strong instrument to study the atmospheres of these planets and learn more about their composition, dynamics, and potential for hosting life. The $10 billion telescope is the world's most advanced space observatory and is expected to revolutionize our understanding of the cosmos, providing scientists with the tools they need to explore the mysteries of the universe. The James Webb Space Telescope has already made significant contributions to our understanding of the universe, including the discovery of the most distant galaxy ever observed. With its ability to study the atmospheres of exoplanets, it holds the potential to answer one of humanity's most profound questions: are we alone in the universe? As the telescope continues to collect data and make new discoveries, it will undoubtedly provide scientists with valuable insights into the nature of our universe and our place within it.